So, hi everyone, I am Giuseppe Longo, I'm a first year PhD student, and I want to explain the possibility to implement the stretchable sensor, strain sensor for human activity recognition or other healthcare solution. First of all, I'm part of a mixed lab in Salerno, from the University of Salerno, that is in the southern part of Italy. Our research topics are diverse. They span from hardware accelerators to device characterization. And one of our research topics is about the sensor solution for healthcare and sport. Through this fourth figure, I want to show to us my sensor in the first figure, two possible applications like in the healthcare and sport environment, and the possibility for future work to implement machine learning algorithms or other deterministic algorithms to perform some healthcare and sport algorithm and evaluation. So first of all, a little bit agenda. I want to start with an overview of a wearable stretchable sensor, then the sensor that I use, that a commercially available sensor. We start a few months ago, so we does not to produce yet our sensor, then the setup, measurement, and results in order to provide some possible application of this type of solution, and in the end, some outline. First of all, nowadays, wearable stretchable sensors are used for different type of applications, like, for example, infrastructure maintenance, also human activity recognition or range of motion evaluation, but also for vital signal monitoring. In the latter figure, in the bottom right part of the slide, I represent the knee pad that I use and the sensor that I use for acquiring capacitance value. But why to use this type of sensor? First of all, because they are low cost. In fact, we could produce it with additive manufacturing. To this day, different talks have been focused on this type of application because they are lightweight. So if we think on garments, suits, or other that could be sensorized, they could be also used in comfort, and in the end, their flexibility. So, for example, for human movements or human tissues and so on, they could fit properly for the application. This is the sensor that I use. As I said, is a commercially available device. It is a capacitor. So as we know, he has three important dimensions that are length, width, and electrode distance D that could be equal to 0 because it is very, very thin. It is a capacitor, so the factory provides a capacitance to voltage converter thanks to a transmitter in order to give the possibility with a USB dongle, so with a Bluetooth communication, to store and log the capacitance value of the sensor. In order to acquire this, a software was used and evaluated to store a CSV file. This is the setup that we made for characterization because the factory didn't provide a calibration curve for the sensor. So we use a stepper model with a closed loop control to impose some known stretches. An attachment system was developed in order to provide a secured position for the sensor, and thanks to a video camera, it was evaluated the stretch delta L imposed to the initial position of the stretch sensor L0. In the bottom part of the figure, I represent the sensor while stretching and in its really relaxing position. In particular, it were evaluated two different types of tests, and thanks to MATLAB, I could align signals provided by the camera and by the sensor, and we could evaluate, as we can see later, the calibration curve. In particular, it was calculate the percentage stretch delta S percentage given by the well-known formula. In particular, for the camera calibration and also for the film of the scene, for the video importing of the scene, it was used an open source software to lower the price of the system. So a point was depicted on the sensor, and it was followed by the Studi tracker software that permits to evaluate the marker position, so the pixel position of the printed and depicted scene on the sensor, and it could be evaluated the percentage stretch. First of all, we evaluated the drift of this sensor that is not so important in this type of application, but for other kind of application, it could be important and could change the capacitance value. In particular, we imposed the maximum stretch to the sensor that gave a 700 picofarad capacitance value, and after 6 minutes, and then we have a plateau of this type of behavior, we saw only a delta capacitance of 6 picofarad, that is about 1% of the total capacitance value. Then we performed some static tests. In particular, thanks to the stepper model, the control system that we had, we imposed nine static position, and we maintain the position 5, 10, and 15 seconds, considering the application in which we would to use this type of sensor. In particular, this is the linear fitting that we evaluated with the maximum stretch position that we imposed and the first one. In particular, a little hysteresis behavior it was evaluated, and in the dynamic test it could be seen better. In particular, we imposed a cyclic test because we would to use this type of capacitance device for human activity recognition, but also for gate analysis and parameter estimation. So we suggest the use of this type of sensor that cyclically change the capacitance. As we can note in this figure, from the first stretch to the fourth, we have an area that is highly related to hysteresis behavior. But this behavior, after for a few stretches, it is similar to a linear behavior, so we lose this type of hysterical behavior. But why we had this type of hysteresis, this type of behavior? Because of the viscoelastic nature of the sensor, that is an elastomeric based capacitor that presents two electrodes that sandwich an elastomeric material. So to the energy that is stored, if we can say this thing, in this way into the material in the initial position. Then some result of the calibration that we made on the sensor. From the static and continuous behavior, we could see that the two linear behavior are quite similar. In fact, both the sensitivity and the zero capacitance value, so at the resting position, doesn't change so much. Looking in literature for this type of behavior, we could say that if we start from the well-known capacitance equation, given the isotropic and incompressible dielectric and the same Poisson ratio for electrodes and the electric layer, we could write the capacitance value that is linear dependent on the percentage stretch. As we said in the initial part of the presentation, I would also to focus on the possible application of this type of sensor. In one of my work, I presented the possibility to follow the range of motion in humans with this type of sensor, and we use as reference two open source software that are two neural network based open source software. As we can note, what is the range of motion? The angles that adjoin, that is the part of the human skeleton in which two bones collide, perform into the space. So we say that performing a squat, a man performs some squats, the capacitance value with some calibration curve, thanks to the setup that I represent in the past slide, could perform in a good way the relationship between the angle of the knee, securing the sensor, as we saw in the slides, and we have errors that are in the range of the current state of the art. Another possible application is in the field of human activity recognition. In particular, we developed an image encoding algorithm, in which the raw signal of the capacitance showed different type of frequencies. In particular, we could note a low frequency and a high frequency in that type of signal. Then we rearrange some windows into row and columns in order to have some patterns that are peculiar of different speed activities. Then, to improve machine learning algorithm, we also does not normalize the figure to overcome overfitting problems of machine learning algorithm. But that are not the only possible application of this type of sensor. As we said, in fact, in the raw signal, in the upper figure, we could note some frequencies. In fact, performing some well-known data processing algorithm, like, for example, short-time Fourier transform, we could note as a working activity has two main frequencies that are near 1 and 2 Hertz. These could be used for applying a gate parameter estimation, because, for example, for elderly people, but also for neurological diseases, people change their gate parameters, like, for example, stride frequencies or stride length, that are the time and the length that a classical gate have to be performed. And our future work consists on event detection, like, for example, in a field in sport environment, like, for example, in soccer activity. In fact, as we can note, the activity depicts some kicks that were performed by a man. So the sensor is capable to distinguish this type of activity, and some machine learning algorithms could be developed in order to define a possible application in this type of environment. So which are the take-home messages? That is possible with this commercially available device to follow some sport and healthcare parameters, but future work will better understand the hysteresis problem of this type of devices and to made some sensors for this type of application. These are some references, and thank you for the attention.